This is the 13th video in a series devoted to abstract linear algebra. And today we want to look at a very important result known as the rank nullity theorem. But before we do that, let's recall the following definition. So we want to suppose that V and W are vector spaces over a field K. And then we say that a function t from V to W is a linear transformation if for all v and w and v and alpha and k, we have t evaluated at v plus w is the same thing as t of v plus t of w. So that means that this function is a homomorphism of the underlying additive group that the vector space is. And then t of alpha v is equal to alpha times t of v. So this is how the function t works alongside the scalar multiplication. Okay, so if we've got these two things, our function is said to be a linear transformation. We looked at linear transformations before, as well as the notion of the kernel and the image. I'll let you recall those two definitions if you need to. Okay, so our theorem for today says that if we have two finite dimensional vector spaces, so we have the same setup over here. We've got vector spaces and a function which is a linear transformation. So if in addition those vector spaces are finite dimensional, then we have this nice equation. The dimension of the kernel of t plus the dimension of the image of t equals the dimension of v. V is the domain of t. So this is interesting because the kernel of t is a subspace of V, whereas the image of t is a subspace of W. One is a subspace of the domain, another is the subspace of the codomain. But somehow, under this linear transformation structure, the dimension of these two objects add up to the dimension of the entire domain. And while we're at it, I'd like to point out that the dimension of the kernel is known as the nullity of the linear transformation, and the dimension of the image is known as the rank of the linear transformation. Okay, so let's get to this proof. So we're going to start by noticing that the kernel of t is a subspace of V. So I'll put here, it's a subspace. Great. But the fact that it's a subspace means it's a vector space in its own right. And from previous video, we know that every vector space has a basis. So we can take a basis, and I'll say B is made up of the vectors V1 up to Vm of the kernel of T. Okay, but notice what we have here. This is a basis of the kernel of t. That means, well, it spans the kernel of t. We'll use that fact later. It also means it's linearly independent. So this is a linearly independent subset of vectors from our vector space. But by the last video, we know any linearly independent subset can be extended to a basis of the entire vector space. And so that's what we'll do. So let's extend B to a basis of the entire vector space. Again, that's possible by a result from the previous video. Okay, so let's say B will include, well, let's call it B prime maybe, will include the original vector. So that's what it means by extension. It means you include the original vectors as well as some more. And the extra vectors will be called W1 up to Wm. Great. So that's a basis of the entire vector space V. But now since this is a basis of the entire vector space V, then if we take T and you evaluate it at B prime, you'll get a spanning set for the image of T. So let's write what this is first. This is T V1 up to T Vm, and then we have T W1 up to T Wn, that should be. Great. So this spans, it doesn't span W, well, it might, but we don't know if it spans W. It definitely spans the image of T, though. Well, why is that? Well, the image of T is just the image of any vector from V, but any vector from V can be written as a linear combination of these. Apply the linear transformation and we get a linear combination of these, so that's the span of the image of T. Okay, great. But let's use this fact up here that v1 to vm is a kernel of t. But that means when you evaluate those vectors at the linear transformation, you get 0. So this becomes 0, and everything in the middle also becomes 0. But that means we can immediately contract this to just the w's, or really the t evaluated at the w's. So we've got t evaluated at w1 up to t evaluated at wn spans the image of t. And that's because since all of these get mapped to 0, they don't allow us to gain any vectors that these allow us to gain under the map. Okay, nice. So this spans the image of t. Now we'd like to show that this is in fact linearly independent. And so this is actually a basis for the image of t. But we're running out of room, so let's maybe bring the necessary information to the top and then continue on. So far, we've taken a basis for the kernel of t. We extended that using a previous result to a basis of the entire vector space V. Then we argued that that could be pared down by applying the linear transformation to a spanning set for the image of t. Now we're going to show that this spanning set is in fact linearly independent. But if it's linearly independent and it spans the image of t, then it's in fact a basis for the image of t. Okay, so let's get going. We'll use the standard strategy for proving something's linearly independent. So let's suppose that we have alpha I in K such that alpha 1 T W1 plus up to alpha N T Wn equals 0. And what we'd like to end up with is that all of those alphas have to be 0. That's the condition for this to be linearly independent. Okay, now let's use the fact that we have a linear transformation, namely these two rules over here, to push everything on the left-hand side of the equation together. That'll give us something like this. We have t evaluated at alpha w1 plus up to alpha n wn equals 0. But now we've got a vector that when evaluated by the linear transformation, we get 0. That means that this vector right here is in the kernel. But the kernel has these v vectors as a basis. So that means since this is in the kernel, it can be expressed as a linear combination of these v vectors, given the definition of a basis. Okay, so that means that there exists, I'll call them beta I, which are constants in K, or scalars in K, such that we have alpha 1 W1 plus up to alpha n Wn equals beta 1 V1 plus up to beta m Vm. Great. So again, we have something in the kernel. We expressed it as a linear combination of elements in the basis of the kernel. Okay, but now notice that all of the vectors in the basis for the vector space are exhibited in this equation. Now we can rearrange it so that it looks like a linear dependence relation for those vectors. Maybe it would look something like this. Beta 1 V1 plus up to beta m Vm minus alpha 1 W1 minus all the way down to alpha n Wn equals 0. So we've got a linear combination of all of the vectors in the basis of V equals 0. But since this is a basis of V, it's linearly independent. But if we've got an equation equals 0 of linearly independent vectors, that means all of the coefficients have to be 0. So that means alpha I equals 0 and beta I equals 0 for all I. The most important thing to notice is that the alpha I are equal to 0 for all I. That's exactly the condition that we need to meet for these to be linearly independent. Okay, so not only do we have a spanning set for the image of t, we have a linearly independent spanning set for the image of t. So that means this right here is a basis for the image of t. Okay, so let's erase this, and then we'll notice that we're essentially done. Okay, so now that we've done all of this, we're essentially ready to go. Let's notice that now we can write the dimension of the kernel of t plus the dimension of the image of t equals, well, notice the kernel of t has a basis of m vectors. That means its dimension is m. The image of t has a basis of n vectors. That means its dimension is n. But v has a basis of m plus n vectors. That means m plus n is the dimension of v. And so that allows us to finish this proof. Okay, so let's get rid of this and we'll look at some quick corollaries. So here's a nice corollary following from that theorem in the special case that the domain and the codomain have the same dimension. So that's our setup. We want to suppose that the dimension of v is equal to the dimension of w, and they're both finite. Then the following three statements are equivalent. T is injective, in other words, 1-to-1. T is surjective, in other words, onto. And T is an isomorphism, or it is a bijective linear transformation. Okay, well, let's notice that if T is injective implies T is surjective, then we have something that's injective and surjective and thus an isomorphism. Furthermore, if surjectivity implies injectivity, then we have something that's bijective and thus an isomorphism. So that means the only thing that we need to prove is that 1 and 2 are equivalent. Because, like we just said, if 1 implies 2, then it also implies 3, because we have both of the parts of being an isomorphism. Okay, so let's prove this 1 implies 2. Let's maybe do this forward direction first. I guess I should say 1 if and only if 2. So they're equivalent. Okay, so this is going to start by supposing that T is injective. But let's recall from something that we did previously that T is injective if and only if the kernel is trivial. So this implies that the kernel of T is only the 0 vector. But if the kernel of T is only the 0 vector, then that means the dimension of the kernel of T is equal to 0. That's a 0-dimensional vector space. Okay, but that gives us the following equation. We have the dimension of the kernel, which is 0, plus the dimension of the image of T equals the dimension of our vector space V. And this is by the rank nullity theorem. But then we're given that the dimension of V is the dimension of W. But what do we have now? We've got a subspace, the image of T, which is a subspace of W with full dimension. In other words, they have the same dimension. So in other words, we've got an n-dimensional subspace of an n-dimensional vector space. But that means the subspace is the entire vector space. So in other words, the image of T is equal to W, but the image of T being equal to W is exactly the same thing as it being surjective. Great, and so that finishes this forward direction. Now let's look at this reverse direction. So this is going to be pretty similar. So taking this reverse direction, we will suppose T is surjective, but that tells us that the image of T is everything. That's the definition of surjective. But now we can put that into our equation. So we've got the dimension of the kernel of T plus the dimension of the image. But recall that the dimension of the image is the dimension of W, because the image is equal to W, is equal to the dimension of V. But then we started using the fact that the dimension of V was equal to the dimension of W, so we can cancel those from both sides, giving us the dimension of the kernel of T equals 0. But there's only a single vector space that has a dimension of 0, and that's the trivial vector space. So that means we have the kernel is equal to just the 0 vector. But then by our previous equivalence, that's the same thing as saying that T is injective. Nice. And that's exactly what we need to finish this other direction. Okay, so there's that corollary. Now let's maybe present another corollary. Here's another quick corollary. So we've got a linear transformation T from V to W. In this case, it It doesn't really need to be finite dimensional vector spaces, although in your mind you can still think that they are. Then we have two results that are related. If T is injective, then the dimension of V is less than or equal to the dimension of W. And then if T is surjective, the dimension of V is bigger than or equal to the dimension of W. Both of these will start with the rank nullity theorem. Well, it's a corollary of the rank nullity theorem, so that's kind of obvious. And then we'll look at special cases. Okay, so let's look at this first case. So the first case is if T is injective. So let's recall if T is injective from what we saw previously, that means the dimension of the kernel is 0. So in other words, we have the dimension of the image of T is equal to the dimension of V. Now last time the dimension of W and V were the same. We no longer have that. Okay, so now the image of T is a subspace of W. That tells us that the dimension of the image of T is less than or equal to the dimension of W. But now putting this all together, we see that the dimension of V is less than or equal to the dimension of W, which is what we needed for this one. Now let's do this other one. So if T is surjective, then the dimension of V is bigger than or equal to the dimension of W. So if T is surjective, the image of T is all of W. So that means this equation turns into the dimension of the kernel of T plus the dimension of W equals the dimension of V. Okay. But now we don't know what the kernel is, but it's at least 0 dimensional. So since the dimension of the kernel of T is bigger than or equal to 0, that leaves us with the dimension of W is less than or equal to the dimension of V. Okay, so that establishes both of these. Okay, so now let's get rid of this, and I want to point towards a more general version of the rank nullity theorem, which would work with infinite dimensional vector spaces. We won't prove it here, but we'll prove it later. So here we'll set up the basic idea of the extension of the rank nullity theorem, which is satisfied by any vector space. So we've got two vector spaces. They could be infinite dimensional now. Linear transformation between them. Then let's specifically look at the kernel, which is a subspace of V, and the image, which is a subspace of W. And notice that there is a very natural injective map from the kernel of T to V. Since the kernel of T is a subspace, that injective map really just sends anything here to exactly itself. So we looked at inclusions like this when we were exploring direct sums. Okay, there's also a very natural surjective map from V to the image of T. What does it do? It just takes V to TV. So it just evaluates the vector at the linear transformation. So what's this generalization? Well, it says that our vector space V is isomorphic as a vector space to the direct sum of the kernel of T with the image of T. So if we took dimensions of both sides, we would retrieve that rank nullity theorem. Here we would get the dimension of V. Here we would get the nullity plus the rank. That's exactly the rank nullity theorem, but this is a version of it that doesn't appeal to having a basis or even having a dimension in the first place. Actually, this kind of idea extends to many different algebraic structures. Okay, so let's get rid of this, and then we'll do an example and leave you guys with some warm-up problems. Okay, so here's an example. Let's define a linear transformation T from P2. Recall that's all polynomials of degree less than or equal to 2 to the real numbers by T evaluated at f of x is the integral from 0 to 1 of f of x dx. Okay, so we need to investigate the kernel and the image and then compare those to the dimension of the domain. And what we're trying to do here is show that the rank nullity theorem is indeed satisfied. Okay, so let's start by looking at the image of T. Okay, so I'm going to claim that the image of T is all real numbers. That's actually pretty easy to do, and that's by the following argument. So let's take, maybe I'll just call it the number A, which is a real number. So I'm choosing a real number arbitrarily, and view a as a plus 0 times x plus 0 times x squared in P2. Okay. And then let's notice that we have the integral from 0 to 1 of a dx is equal to ax evaluated between 0 and 1, which is a. So in other words, we found a preimage, which is this thing right here, of our element from our codomain R. But that's exactly what we need for this to be onto, in other words, surjective. So we have the image of T is all real numbers. Okay, so in other words, this thing is surjective. The dimension of the image is 1 because R is one-dimensional. Okay, so now let's look at the kernel of T. This is going to require a little bit more work, but let's get to it. So let's suppose that f of x, which equals ax squared plus bx plus c, is in the kernel of T. Okay, but notice that means that the integral from 0 to 1 of f of x dx equals 0. That's the entry fee to be in the kernel. You are evaluated at our linear transformation and get 0. Maybe we could put that step in the middle. T evaluated at f of x equals 0, and then that's the rule for T. Okay, but then we can plug in the version of the polynomial with these coefficients. That gives us something like this: a over 3 x cubed plus b over 2 x squared plus c x evaluated from 0 to 1 equals 0. Something like that. Okay, but now what we can do is evaluate that, and we'll get a over 3 plus b over 2 plus c equals 0. But then notice what we have. We've got an equation that tells us the relationship between a, b, and c if we get something in the kernel. Namely, we see that c is equal to minus a over 3 minus b over 2. So that means f of x has the following form. F of x is of the form, let's see, ax squared plus bx, and then minus a over 3 minus b over 2. Okay. But notice that tells us that f of x is in a spanning set where we set each of those equal to 1 at a time. So we've got a spanning set where kind of the a term is 1 and the b term is 0. That'll look like this: x squared minus 1/3. And then we've got another element in the spanning set that's for the b term. So that'll be x minus 1/2. Okay, so notice that this ax squared plus bx minus a over 3 minus b over 2 is definitely in the span of these two. You just weight this one with a and this one with b. Okay, but that means that this spans the kernel. But then you can also check easily that these are linearly independent. So this is in fact a basis for the kernel of T. Okay, so let's see what we've got. We have the image of T is all real numbers. The image of T has dimension 1. The basis for the kernel of T has 2 elements, which tells us that the kernel of T has dimension 2. Then the kernel plus the image, the dimension of the kernel plus the dimension of the image, 2 plus 1 is 3. But 3 is the dimension of P2. So yes, the rank nullity theorem is satisfied. Okay, so let's get rid of this and I'll leave you with some warm-up exercises. I'll leave everyone with 2 nice warm-up problems built off of what we've seen, and both of these are to show that the rank nullity theorem is satisfied in these 2 cases, which of course it will be because it's a theorem that we proved. Okay, so let's start with a linear transformation from K3 to K2 defined by T evaluated at x, y, z is 2x plus 3y, 3y plus 4z. And so maybe do this for a couple of different examples of base fields, maybe real numbers, F3 and F5. Maybe some more if you'd like to see if you can get some different numbers out of the kernel and the image. Then we've got this map D from P3 to P2. So these are, let's see. So these are polynomials of degree less than or equal to 3 to polynomials of degree less than or equal to 2. And here, our linear transformation D takes f to f prime. In other words, the derivative. And again, maybe do this for two cases. Let's first do this for the case when the ground field is R, and another case when the ground field is F3 again. I think you get something different in each of those cases. Okay, that's a good place to stop.